And yeah, I guess we can slowly start. So yeah, as you can see, we keep it casual. It's meant to be a meetup, so that we actually get to meet each other, hopefully on a regular basis. And yes, exactly, classic MS Team stuff. Yeah, and actually, we would like to start with Lindsay. As you know, he's the author of xeokit SDK, and everything started with him even before there was even WebGL with the predecessors of xeokit. So there were a few iterations to get to the point where we are today. And then, yeah, I hope, Marta, you are
yes, exactly
supporting Lindsay. Okay.
Yeah. Yes.
Hi.
So,
yeah, sorry, the link
hi,
kept
Lindsay.
taking me to the xeofix. This time it worked.
Okay, great. So we have you on board. So as I just mentioned, Lindsay, you're the author of xeokit SDK, and yeah, originally from Christchurch, New Zealand, but not calling from there today. I guess MS Teams wouldn't handle it such a distance. So
Didn't last
from
time.
Berlin, yeah. And without further delay, I would just give you the stage, Lindsay, to welcome everyone and to share some words about the SDK. Stage is yours, Lindsay.
Sure. Hello, everybody. Let me just start by sharing my slides. Slides. Can you see my screen?
Yes.
Yep. Hi. Well, I'm Lindsay Kay. I'm a graphics software engineer. I'm originally from Christchurch, New Zealand, and I've lived in Berlin since around 2010. My background is in building 3D graphics libraries and applications for visualizing engineering and medical data in the browser. And so that's what I've been working on for the past 15 years or so, mainly making open source tools to support this. I started making xeokit about 5 or 6 years ago, based on lessons learned from previous open source libraries and WebGL projects I've worked on for visualizing medical data sets, and more recently IFC data sets. And so over the years, I've made a few open source libraries like CNJS and xeogl and so on. So I started xeokit about 5 or 6 years ago, and then me and xeokit joined Creoox in 2020, and since then xeokit is maintained by the team of us at xeokit, and we're a mixture of different kinds of engineers, civil engineers and software engineers, and civil engineers who have sort of transitioned into also being software engineers in the civil engineering domain. So that gives us the domain knowledge, and we work with and for engineers to help them visualize things on the web. And so some of the challenges in visualizing on the web is, of course, loading really large models quickly and interacting with them smoothly in the browser on all sorts of devices with all sorts of capabilities and strengths of GPU and so forth. We have to manage memory very carefully, and we have to make the viewer interactive for like hundreds of thousands and if not millions of objects. And we also have to render these engineering data sets with the full geometric precision, which GPUs do not tend to support. Your desktop GPUs are only accurate to about 7 or 9 decimal places, and so we need to be able to visualize models with really large coordinates accurately without that loss of precision from rounding. So what is xeokit? It's an SDK in JavaScript, and it supports visualizing a bunch of different AEC file formats, and it's designed to be approachable for engineers. It's designed in the domain of people visualizing models for AEC. And so yeah, and so that's just a little code snippet that just shows the really simple, minimal little model viewer app with xeokit. How it delivers performance. We have our own native file format, which is binary. In addition to be able to load in GLTF and CityJSON and .bim and so forth, and IFC, we can pre-convert those file formats to our own native binary format if we choose to, if users choose to, for fast downloading. We also, we've built xeokit from the ground up, not using any other WebGL frameworks, because we need a level of performance and a low memory footprint, which wasn't really available at the time when xeokit was conceived, and so we design it from the ground up to render these large models efficiently, and we're constantly tuning it using real models from BIM. And the other thing that we do is, yeah, as I mentioned before, we render double precision coordinates accurately by using a tiled relative center coordinate system within the viewer, which is transparent to users. Yes, what else? Oh, yep, so just some slides on the differentiators of xeokit. This is what happens when you take a model with large coordinates and you render it on sort of on a WebGL viewer that's not designed to handle large coordinates. And on the right, we've got xeokit doing sort of double precision emulation using relative center tiles. So that's a model that's positioned like hundreds of meters from the coordinate origin at its real-world location in Lyon, France. Okay, I won't get too deep into this. This is just a little bit of the technical details on how we compress models. Another thing that we have in xeokit, that's one of our differentiators. We also care a lot about the usability and ease of interaction with models and navigating them. So we have snap to vertex. That's just one of the sort of features we're kind of proud of here. Snap to vertex and snap to edges. And also, this is an example of a contribution from our partners. So the algorithm for this was devised by Tony Marty, who is working with one of our partner organizations. xeokit also natively integrates IFC semantics to help you navigate your models. And it allows you to load lots of models into the same viewer in such a way that they federate together and combine together to form one big model. So you can load models from the different AEC stakeholders into the same viewer, like electrical, mechanical, and so forth. And we have our own product built on xeokit. We have XeoVision, which is a viewer, a cloud-based viewer running on xeokit, and it uses most of the features of xeokit SDK. And yeah, you can use that as an example of what you can do with xeokit. And you can even also, of course, use it as your BIM viewer. Our philosophy is transparency and openness, and we release our xeokit under AGPL3, and full source code is available on GitHub. And yeah, we listen to community feedback, and we're always interested in your suggestions, pull requests, and so forth. Yeah. Yep. Looking ahead. Yep. There it is. We're just a few things that we're looking ahead to do: streaming and more plugins. Yeah, more tools. So that's the wrap up. xeokit is a high-performance open source SDK for building AEC visualization applications in the browser. It's built from the ground up to tackle challenges of scale, precision, and fluid interactivity, and it evolves with the community and Creoox. So thank you very much, and that's me. I'm gonna stop sharing.
Thank you very much, Lindsay. Yeah, that's very exciting. And yeah, as you can see, the community around open source projects is quite important. That's why we are also here. But it's also this kind of proven over the years type of technology in use in many enterprise applications, which makes it quite stable. So it's not thrown away after each version, so to say. So yeah, under the motto of getting started with the first iteration of the xeoMeetup, we have prepared also something new, something that we've worked on in the past several months. Although it's quite easy to work with xeokit as it is right now, we've heard some feedback also from the developers that it would be nice to have also web components for xeokit, and that's what we've been working on. So in the second part, Marcin, stage is yours to show us a bit more.
Yes.
What we can do there.
Yeah. Yes. Hello, everyone. Let me share my screen also. Yes. Can you see the screen? Here's the blank page, and the VS Code editor.
Exactly.
So yeah, so we built xeokit Web Components to help make it easier to add xeokit viewer into your page. So here I have this empty template, and here what I do is I load xeokit Web Component from the CDN. So that's the one package we need to include. And then simply by adding xeoviewer component to the page, and then embedding xeomodel with those 3 lines, we have working xeokit viewer. So here we can add a lot of functionalities. So we can, sharing.
That's expected on Mac.
Yeah, so screen. Yeah.
Yep, still there.
Okay, so yes, so
no, broke again. Okay.
Yeah. So let's make the viewer transparent.
Nope, disappeared again. Okay.
Yeah, so here we can make it transparent so it doesn't change affect your page styles. And then what we can do next? We could like change the position of the nav cube, or even disable it if we don't want it. So and all of those attributes are described in the README on the GitHub. So bottom right. Okay, so we can load more models simply by adding another Xeo model into the xeoviewer web component. So let's go do that. So here we load the point cloud model matching our building. So here the building is loaded, and now the point cloud is being loaded. Takes a while because there's a lot of points. So here you can see that the point cloud matches the building. What we can do, we can let's say show the edges simply by adding show edges to true, and it will enable the edges of the entities. So let's then there's a lot more. We can add the bounding box. You can check all of the attributes in the README. So quickly to demo that. So the next wanted feature is to add the tree view. So we can do that simply by pasting the tree view panel and then embedding inside the tree view xeotree view web components. So with the different types of hierarchy. And yep. So and it loads the point cloud and it will appear in the objects here, and then we can enable or disable some models. We can check the classes or the stories. So this this model is not good to show the metadata. So let's switch to some different model. Let's say duplex. Yeah. So this is the duplex model. Here we can see all of the different classes, stories, and the objects described in the IFC. So, okay, let's disable this bounding box for now. So the next thing, more advanced thing, like if you would want to have some callbacks. So this is like adding JavaScript, but this is like the desired feature. So let's say we want to have some action when we click on some tree view nodes. So we add this callback, tree view node clicked. Let's add it to the all of the tree view nodes. And then some JavaScript to have this functionality. So we would want to, if we click on some tree view node, we will select all of the nodes within. So script, and so this is the callback function which we described here. Preview node title clicked. So first thing, we unselect all of the objects on the scene, and then we select all of the entities within the tree view node. So let's try that out. And we go classes, and let's select all of the doors, walls, windows. So that's it from my side. You can see basically with few lines of HTML, you can have xeokit viewer embedded in your site.
Great. Thank you very much, Martin.
Thank you.
One short question from my side. Before we continue, you can also load an IFC model, right? Not just
exactly.
an XKT.
Exactly. This all of this is described on the xeokit Web Components GitHub page. So yeah, there we can load GLTF, GLB, LAS, OBJ, STL, .beam, and IFC. IFC uses our WebAssembly converter, so it converts it on the fly. And then
will share more details about that. Yeah. Okay. Great. Thank you, Martin. So yeah, as you just heard, IFC has to be converted. This is one of the main formats that we're working with. But when you visualize in the browser, you have to, or in at all, you have to display triangles somehow. And IFC doesn't have these triangles inside, so the geometry has to be converted. And this is what we are typically doing with our cxConverter. Fabian, stage is yours.
Yeah, hi everyone. So the converter is one application that has only one purpose, to load IFC models into xeokit. And it runs in batch mode, so it's a console application. You can download it from GitHub. The address is here, github.com/Creoox. From there you can find it and download and test. So from IFC is a semantic model with geometry and metadata, and it's a very complex model. And the converter has the purpose to simplify that and convert it into a format that is usable for xeokit. So the geometry is converted into GLTF, which I will describe in a minute, and also to JSON, which is directly available to read in any JavaScript application. And the converter is very simple to use, just the converter input file, output file, metadata file. And there's also a config file, a JSON file with settings. You can set certain features and settings, which I will also talk about later. So here on the left side, you see the IFC universe. It's very complex. It has many different geometry types. And this complexity is kind of filtered and buffered and converted into a very simple geometry model, which is easy to understand, which is easy to handle further in xeokit. So GLTF basically has only triangles, material information also, of course, in the node hierarchy, but the geometry model itself is very simple compared to IFC. So IFC mostly has extruded shapes, 2D cross sections, parametric shapes, and extruded shapes, NURBS, all kinds of geometry types. And a lot of it is even redundant. There's a lot of redundant information, and the converter and any IFC viewer actually has to figure out which information has to be taken and which has to be ignored. And yeah, it's very messy. So there's a lot of models out there that have problems, that have issues. Sometimes it's correct, sometimes it's not correct, because different authoring tools generate these IFC files. And all this complexity is handled in the converter. And we worked through many issues already together with customers where there were bugs or something missing or some models had issues. So we worked through many of these issues already and continue to improve and continue and improve the converter. Yeah. So a few words about IFC. Industry Foundation Class is an open standard developed by an industry association called Building Smart. On that website, buildingsmart.org, you can find all the schemas to download and lots of documentation. And it's the file format is an open format. It's human and machine readable, which is a big benefit if you want to troubleshoot something. You can always open it with a text editor and see what's going on in the file. Here's an example how it looks like. This is from an IFC model when you open it with the text editor. So each line is one object, and each line consists of an ID, a data type, and then attributes. In the second line, for example, you can see a string attribute, a number attribute, and down here the green selected number, that's a reference, so it references another entity here. And this is how all the entities and even the geometry is defined in IFC. So very easy to understand, but the model gets very complex when you go into the details. So there are different file formats that you can use to store IFC models. The most common is .ifc. It's just a text file with the example that we saw before. That was an IFC file. There's also IFC XML, but it's not actually used in practice. Then there's IFC zip, which is just an IFC file compressed in the zip format. So you can manually just compress any IFC file to zip and then rename it to .ifc zip, and then every IFC viewer can directly render it. Also, the converter can read those files. And the advantage, of course, is that you can save a lot of disk space if you use that zip format. Quickly about GLTF, as I said, it's a very simple format in a JSON format for storing geometry. There's also a binary format which we recommend to use. It's the same content, but it's all compressed in one binary file with the file extension GLB. So it's the exact same information, the exact same data, but it's easier to handle, and it's a very small. It's smaller, so it also saves disk space. The converter has lots of features. I will not go through all of them here. You can find it on the website with the link that I showed before. It should be also in the comments. And there you can check out the features. You can test the converter by yourself by just downloading. And if you have any questions, please contact us or ask directly here in the meetup. All right, from there, from GLTF and JSON, the conversion pipeline continues to xeokit SDK, and I will hand over to my colleagues to talk more about that part. All right.
Thank you, Fabian. So yeah, voice passed to Mateusz. You're still muted.
Okay, so I can take over from
Yes.
Fabian here. So typically, for let's say for the user of xeokit, we recommend that like standard pipeline, which contains two steps. One is this conversion from IFC file to GLB, and of course the metadata, so all this semantic information about the models, like properties of the door, whatever. There can be very, very different information stored in the meta model. So that's the output of this cxConverter, what Fabian just presented. And then the second step is to convert further to optimize format for the xeokit. It's called xkt. Lindsay already mentioned it. Maybe Lindsay, you can also mention a bit about advantages of the xkt format over plain GLB.
Okay, so xkt aims to kind of pre-digest the geometry information so that the viewer does less work while loading it. And one of the things that xeokit does to minimize the payload size and so that the viewer doesn't have to do it is it will convert the double precision coordinates into tiled relative center coordinates within the xkt file. And that reduces the numbers for the coordinates from needing 32 bits down to needing 16 bits. So that's just one compression technique used in xkt.
Okay, thank you. So this is what we recommend to go to convert to xkt. It also adds some other features, like you can combine the metadata into one single file. So for the file handling, it might be a bit easier than to keep track about all the metadata in the JSON. Not always this is the best solution, because if your metadata are huge, really huge, then it will impact the performance. So you'll always have to take some decision. There are pros and cons of each approach, but generally, if you optimize for like viewing the models, then going through this backend conversion pipeline from IFC to GLB and further to xeokit, it's what we recommend. But quite recently, we also try something different. So we actually compile cxConverter into the WASM. So for those who are not familiar, this is like binary format which can be executed. So you can compile from many language to one binary format in form of the bytecode, which then can be executed. And there are many runtime, and nowadays all the browser actually are able to execute. So you can take your native code and run it, for instance, in the browser. And we did the same for the cxConverter. So compile the C++ code, and we can now run this in the browser. So as you see here, we read the IFC file, do the full conversion to triangulate this IFC model and render it in xeokit. Like from the technical side, it's, let's say, not very difficult. What you have to do is to include this like binary format. You can do it using typical NPM distribution channels, which provide special bindings for this WASM compile converter, and then we prepare plugin in xeokit, which then can be initialized and set this compiled version of the converter, and then you simply can render the model directly from the IFC. The API of the cxConverter for the web is for now very, very simplistic. So you just take the data, which means in this case IFC file, and the output is GLB, actually, not GLTF, plus metadata. So you can do whatever you want with that. Yes, I think this whole notion of running a native application inside the browser is now quite hot topic. Recently, WASM has been version 3.0 has been released, which extend memory to, I think, 64 bits. And yes, so this give you more and more possibilities. For now, it's like, for us, it's like start this journey to see what we can build. Like one obvious use case is when you want to keep your IFC model local. So you don't want to send this to the server. That's quite typical use case for now. But in the future, we might also find more use case, more scenario when such in-browser conversion is used, especially if you have more and more memory. Because so far it was just 4 gigabytes memory for the WASM runtime. Now it's in the web is 16, so it's open new possibilities. Yes, I think that mostly if you want, you can play with this converter examples on the xeokit examples. So yeah. Thank you.
Thank you very much, Mateusz. I will take here maybe a couple of questions on the chat. I think they're quite connected here to the topic, and we can just follow on them. So yeah, if I understood correctly, with this WASM or WebAssembly loader, you can directly load an IFC without any server, without any backend conversion. So this is like the main advantage here. But yeah, so the question is, if we skip the convert to XKT here, so do we actually get any files, or are we just loading into the model? The question from Miguel.
Depends what you define as a file. You have this data and you can save this to the file. But this is when you render, it's directly passed to the viewer, so you don't get this file directly. But if you play with, so if you're using the approach which I demonstrate over the xeokit cxConverter IFC plugin, then you will not get any file. You will simply load this model into the xeokit. But if you use this API, this API which I'm highlighting right now, this is binary buffer, and you can save it to the file. It's really up to you. You can save it to the file. You can save it to the local storage. It's really up to the user here.
Okay. And then I guess this is like the pros and cons of using WASM Loader or this WASM converter version versus the typical backend converter, where you can, on the backend, you can split even larger files into smaller files, so you can handle even above 1 gigabyte. And as I see here, the question from Jaden, an IFC file of 1 gigabyte would be better to convert with the with our CLI cxConverter with the C++ application on the backend in chunks, and then load it as XKT.
I fully agree. Actually, if you don't want to use your own, let's say, backend conversion, we have something like Xeos services where you can actually, from the browser, make a call, and then this is fully managed service by us. In return, you will get the link to the file, and you can use it in xeokit directly as well without backend conversion as an alternative here. Of course, you will wait a bit, so it's not like for free, but for the conversion in the browser, you also will wait. Yes, because that's a trade-off. You optimize your local needs over the time of getting the model being rendered.
Yeah, as you can see, guys, we have so many topics. It's not so easy to put everything into one meeting, but you just took a glance at these new services. I think this also touches the topic of converting from IFC directly to XKT, because with Xeo services, you can do that without having to deal with the intermediate format. This question from Michael. So I suggest that we move on with the next topic. And please, guys, if we didn't address any of these questions, let's do that after the next part, which is something new, something where we just experimented to see what we can do, what we can achieve. And we combined 2 open source projects together. The topic is point clouds. Reality capture is a hot topic nowadays, and we get to deal with more and more data, exceeding the browser limits for sure. So exceeding the typical loaders that we support to load point clouds. So then we have to go into direction of streaming and lazy loading, progressive loading, however we call it. And this is what Michał is going to show us. So Michał, the stage is yours.
Thank you, Dian. Thank you. Hello, everyone. My name is Michał. I'm a software developer with Creoox and working mostly on the xeokit SDK. And today I'm going to give a short presentation of the Potree format and xeokit SDK integration that we've been working on recently. As Lindsay already introduced us to the xeokit SDK, so I'll begin with an introduction to the Potree format. And since Potree format is used to define point clouds, let's see how a point cloud looks like. Here is an example of a point cloud rendered with the xeokit SDK. A point cloud is a rather technical term for a set of points, including their 3D coordinates, their colors, intensity, and potentially some other attributes that define a single point. When I zoom in, we can see how what from far looks like a set of objects basically is in reality is a collection of tiny little dots that make this kind of sensation of real shapes. So that's an example of a point cloud. And point clouds in practice are obtained, for example, by scanning with a LiDAR or through photogrammetry. And what we get in the process of those methods is this collection of points that defines a surface of an object or some larger environment. Another example of a point cloud is here. This building is also, if we zoom in, we can see that it's composed of tiny little dots, not real meshes. So it's this sensation that makes it look like an actual object. Now, as you can see, xeokit already supports point clouds that are stored in either the LAS file format or the xkt file format. However, those currently implemented features of the xeokit SDK, using them limits the, or rather, the point cloud needs to be loaded completely into memory to be rendered, which means that if the data size doesn't fit the browsers or the GPU's available memory, it cannot be displayed. So this is rather serious limitation for some of the applications. As we know in practice, the large data sets are not that uncommon. So that's where the Potree format comes into play. And Potree is an open source project based on academic research, which provides a couple of GitHub repositories. This is the main repository, which implements a 3JS based viewer or renderer. But on top of the viewer, the Potree project also implements a Potree converter and a Potree format. So the Potree converter, what it does is it converts an original file, like for instance, LAS file, which xeokit SDK already supports. It converts it into the octree data structure, which helps rendering those large data sets in the browser. And that means that the size of the data set is effectively unbounded, or rather bounded by what a server that hosts such a data set allows. So, as I said, the Potree format organizes the data into an octree data structure. And what is an octree? Here is this image from Wikipedia that shows this organization of an octree, which takes a volume and splits it recursively into those groups of 8 smaller regions. And effectively, this creates this tree of smaller and smaller nodes, each of which contains more denser and denser sets of points. Now, in the context of a 3D renderer, this organization allows for specific regions to be loaded individually on demand, which is an important feature, depending, for instance, on their visibility in the view frustum or on the distance from the camera, and also unloading some of the nodes that are not needed at some moment by the browser. So we'll see this in a moment in practice. But first, let me show you briefly what is the output of the Potree converter. And for this proof of concept work that we did for xeokit integration, we focused on the version 2 of the Potree format. And in this version 2 of the Potree format, the output of a conversion process of, for instance, LAS file is 3 files that define the whole point cloud. The first file is metadata JSON, which defines a structure of a point cloud. So one of more important things is the set of attributes each point is defined with in the point cloud. This is a position, but also some optional ones, like, for instance, intensity, or some classification, or finally a color of a point. On top of the metadata JSON file, there is also a binary hierarchy file, which defines in a binary form some the structure of this tree. And finally, there is this octree binary file, the largest one of the tree, which defines the specific data for each of the points. So here is this proof of concept work implemented in the browser, and the model is Hala Stulecia in Wrocław, also known as Centennial Hall. And this viewer here is based on the reference Potree viewer as defined by the original project, GitHub project, where the left-hand side is a canvas rendered with Three.js, like in the original Potree viewer. And on the right-hand side, we have a canvas that is rendered with xeokit SDK. There are slight differences in how those renders look like because of slightly different configuration of the renderers and slightly different features that they support. But the point of the proof of concept was to be able to drive a xeokit SDK renderer with the data from the Potree format, to integrate both together, not very much on the actual aesthetics or tiny nuances of how the point cloud is displayed. So while I navigate here, there doesn't seem to be anything extraordinary happening in the scene. On the surface, it looks like nothing special is going on here. But let me zoom out a little bit, and I'll toggle here a display of bounding box visibility. And bounding boxes are those kind of extents of single partitions, like are also schematically drawn here. So every individual region that can be loaded or unloaded from the Potree format has its own bounding box, this extent, which is visualized with those yellow lines. And as you can see, if I zoom in, more of those boxes appear, which means more of the regions are loaded and also rendered in the scene. It's very smooth in how it looks, because the algorithm relies on a distance from camera mostly to drive visibility of those regions. So as we get closer to a region, more nodes, more of its internal nodes will get loaded into the view. As I rotate here, you can see some of the distance nodes disappear and some of the closer nodes appear in the view. So this is the main principle of the integration of a Potree format with the 3D renderer and 3JS or xeokit SDK renderer in this case. And the key kind of feature of this integration is that by unloading or by managing the only a limited number of nodes being visible at the moment, and potentially unloading some of the nodes that are not visible at some time, this helps to keep the JavaScript and WebGL or GPU memory footprint in check as this footprint approaches some given threshold. So a developer can specify what should be a maximum amount of memory used by some model, and the logic of this approach will evict some of the nodes whenever this available memory threshold is being approached. What we can see also, we can observe this kind of phenomenon here in the network panel. If I start zooming in, we see how some requests appear to the server, asking for those new regions to be loaded into memory and then into the 3D model. Now we can also,
so Micha, to summarize, you can constantly load and unload parts of the model, so that basically you can visualize many gigabytes of point clouds that would otherwise be impossible to render, correct?
Yes, yes, that's correct. The web page only holds in memory what is supposed to be visible in the scene. So if there were some far regions out there, they would potentially get evicted from the memory. And
okay, cool.
It
out of curiosity, how many gigabytes have you managed during the POC to render?
There was some other model that we tested with over 6 gigabytes of size. This one is not very huge, but in reality, the size of the model is only limited by what the web server can host, because the browser manages its memory, or rather the viewer manages its memory. One more interesting thing is because the data is hosted in a single file, the particular regions are being accessed with the content range header, which limits which bytes of a file served by the web server are to be retrieved by a given request. Yeah, and the consequence of this approach is that those data files can be hosted on any web server, really, any static web server. This feature doesn't require any specific web server handling. It's a static file that's accessed with the content range header, which most of the web servers provide or support. Yes, and so yeah. One last note is, please be. It's important to know that this work is by no means a production grade code. At this stage, it's only a proof of concept, which we would improve on in the future. Okay, so that would be all from me. Thank you, and
Thank you,
back
Michał.
to you, Dian.
Yeah. Thank you very much. And please, guys, give us feedback about this POC. That's why we do it, to see if there's interest from the market, from the users, to go further in this direction. We know that we can do it, but of course, we always have to prioritize our limited resources. So yeah, taking a look at the clock, I guess we have reached our 60 minutes. Still, of course, anyone who would like to stay, we can address some of the questions that we have already in the chat. And yes, thank you. Thank you, guys. So yeah, I would then open the Q&A session, and thank you. So I guess starting from top to bottom, yeah, we've touched the XKT direct conversion from IFC to XKT. I think we don't plan to have it in the binary, but we have it already in the Xeo services, so it's basically already possible. It's still this kind of two-step, but packaged into one service, so it's much easier to use. So yeah, be sure to get in touch. We can share more details on that. And then what is the maximum size limit for IFC for the cxConverter? Do we have an answer for that? Yeah.
There's no limit, actually. The limit is your compute resources, RAM and disk size. But other than that, there's no limit. Our biggest test file that we have right now is a 2 GB IFC file from Baku Stadium. We saw it in Lindsay's screenshot, and it renders quite smoothly in xeokit. So 2 GB is not the limit at the moment. It works quite well.
Yeah. I've heard from one university in Switzerland that they've managed to convert and render 25 GB IFC, which was, I think, also LiDAR scan of a railway track. Not smooth, but still managed to render. So we are constantly pushing the limits. But yeah, in praxis, it's not just the file size, it's also the complexity of the geometry, right? So yeah, I hope
in theory, you can have a very small file with just a few megabytes and generate huge amount of triangles with that. It really depends on the way how the geometry model is described in IFC.
Okay. Next question, do cxConverter and xeokit convert benefit from a GPU in the conversion pipeline?
Not that we
No,
know
it
of.
doesn't. Yeah.
Not yet.
Not that we know
Maybe
of.
in the
Yeah.
future.
I mean,
Straightforward answer. Mhm.
I mean, to use GPU for the calculation, you need to very specific like logic there, and yeah, so to use it, you need to have a different way to approach what we are doing inside conversion pipeline. So it's not like straightforward to offload this to GPU, but yeah, everything is doable. It's just a matter of pros and cons.
Okay. And then next question is, I guess this answers this one. I have multiple xkt files that are 100 megabytes each, and every time it takes 30 seconds to load, how to do caching in the browser. So I guess
there are HTML APIs for local storage that you could use. Yeah, it's a bit it's outside the scope of xeokit really, but yeah, you could definitely use local storage APIs or
yeah. This is like the application layer where you deal with files. Yeah. Okay.
Yeah.
Then our customers are getting larger IFC files. Okay, yeah. xkt files are getting larger. Is it possible to stream data? Maybe just one comment here on the larger xkt files. We had an update in the xkt versions where we've changed the compression. So maybe share a couple of words about that.
I can just mention that right now xkt by default is not compressed, so you actually can use the web server compression. That's what we recommend because it's more efficient than relying on the decompression inside like JavaScript runtime. So that's so one way to deal with the bigger files is actually to use compression on the web server. It's fully possible right now.
Yeah, and by compression we mean zipping.
Yeah. Zipping, yeah.
Yeah. Okay.
Yes, and of course you can also further manipulate what you really have in this in the file. So if you have some like not critical elements, you can filter them out. You're gonna have a smaller xkt there or GLB. So there are also some other way, but then you are losing the information. But compression is lossless.
gzip, yes, exactly. Yeah, we found out that overall the performance is better when you don't perform these steps and you leave it to the HTTP compression. Yeah. And then, yeah, the next question is it possible to stream xkt data? Actually, maybe I can unmute you, Michael. Would it be fine? I hope so. Yeah. I think you can now ask your question.
So what I mean by streaming is now you get the entire model, even if you're only looking, for instance, at the front of the building. So streaming will require a backend service that is able to provide only the data that's in the view. So maybe that's in the pipeline. I don't know, but yeah, it could be.
Yeah, I can just simply say that right now it's not possible. You cannot really stream like directly to the viewer where what is needed because there is no like this kind of layout of the content as you have in the octree format. So actually to like effectively, let's say, stream, although it's not technically, it's not streaming, picking, you know, part of the model, it also has to be supported by the like encoding this model in the particular format, and neither xkt nor GLB allows it like out of the box. So unfortunately for now, we have some like ideas, but yeah, it's really not even POC stage.
Yeah, the use case we're focusing on is getting the entire data set into the viewer as quick as possible. Pretty much the whole geometry data set anyway. Yeah, and like the likes of xeokit can then progressively load metadata as required, but we want all the geometry and the aggregation structure of the IFC in the viewer upfront in one shot at the moment, following the use cases we focus on.
Yeah, so exactly. Performance optimization techniques. This is like a huge topic, and we are constantly working on. So we are still brainstorming some answers for that. We have, of course, also always the question mark about streaming, because client-based rendering is basically the opposite of streaming. It also changes the user experience, online, offline usage, and things like that. So yes, many aspects to consider. But yeah, thank you for the question. So I guess we have covered the most important. Okay, there's one more question from Sebastian. When changing the model, Sebastian, would you like to ask your question? Maybe just microphone. Okay.
Yeah. Hi. Yeah.
Hi.
So basically, this is like a follow-up question on the discussion before with the streaming. So before you showed that there is this chunking algorithm on the cxConverter that automatically chunks the model, and so if I now save those chunks in the backend and then on the backend store them in like a database that stores also the bounding boxes of those chunks, is it possible then, from my thinking, that I just load the chunks that are also in the viewport to optimize the performance?
I guess we we typically differentiate between the loading performance and the runtime performance. So we are talking here about loading these chunks. So basically the loading performance, right?
I think both, because of course, if fewer chunks are loaded, then you have less to render and possibly also less to deal with, right? But I'm not the expert there.
Yeah.
So. I think at the moment a split conversion pipeline creates these manifests that list the files that provide the chunks, and the manifest output by the IFC, the GLT conversion cxConverter, contains the bounding volume of the files, but not of the individual files themselves. So potentially we could extend this for the manifest to have the boundary of each of the chunks for a loader to load the chunks within the boundary that falls within the viewing volume. So that's potentially doable, but not currently supported.
Okay, good to know. Thanks.
I think we have mainly focused on techniques like deduplication. So really to see what we can extract out of the client-based rendering without streaming first, and then as a last resort, you can always do that later on, but first you have to be sure that you've done the rest. Okay. So yeah, again, thank you guys for all the questions. Before I forget, please be sure also to follow us on social media, LinkedIn, YouTube, GitHub, as well. Give us a star there too. Oh yeah, okay, one last question from Fabian. Are there any known clients using ASP.NET as a backend?
You have an answer.
Sorry? Yes, we are. Yeah. Okay. That's the community. Yeah. Great. All right. So yeah, it was really fun, guys, having the first meetup with you. And I hope to see you in the next one. So stay tuned and we keep in touch. Okay, one more from Adam. Or not? Yeah. All right. Thank you, everyone. We keep in touch. See you soon.
Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Thank you.